All right, so welcome back for week 2, where we're going to start in on the last 3 chapters of chapter 3, starting with 3.5, which is titled Transformations of Functions. So we talked about all the different things that functions bring for us, and now we're going to talk about the graphs of them and just the basics. As you can see here, I have 3 basic graphs, but then we're going to go ahead and make sure that we can adapt, transform these by adding, multiplying, dividing, doing different things to each and every one of these functions. So I'm going to ask you guys real quick to take a few minutes to try to graph these 3, then these 3, and those 3. Some of the basic graphs, those 9, that you guys should all know how to do. All right. So I'm going to go ahead and pause the recording, give you guys a quick 3 minutes to go ahead and make sure that you remember any and all of these. And I'll minimize it so that you can see them. All right, ready, go. All right, I did the first couple. Those are the ones that I am very confident that all of you know. The rest of these, not so much. All right, should you know them? Yes. Have you seen them before? Absolutely. Do you remember them? I don't know. Yeah, the first 2 I'm very confident in. The rest of these depends on each individual, how much of this you remember. So the square root of x, remember, if you don't ever know any of these, and it started with lines way back in junior high or even elementary school, depending on where you went and your capabilities, we did these little things called t-charts because it looked like a T, and we said, all right, well, all of these are functions of x. And so we chose the x values that we thought would work well, and then we got out the y values, and we called those ordered pairs or points, right? So 0, 0, 1, 1, 2, 2. That's the easiest because it says that x and y are exactly the same. But that doesn't play for every other function, okay? But remember, are all of these functions? That's the power in writing f of x. They're already telling us that it passes the what? That vertical line test. For every one of these x's and everything in between, it would map to only one output or y value. Okay, so for this one, I would have chosen zeros, 1, 2, maybe -1, -2, and got those y values out. And you can see when I go this direction a certain amount, or this direction a certain amount, I went the same in the y. Okay, we'll call that something at the end of today, right? When we get something similar on both sides of 0. But how about the square root of x? Do you guys all remember that one? Very similar to the squared function, right? And in this case, if you don't know, plug in things that you do. So for example, a 0. I know the square root of 0, it's 0. I know the square root of 1, it's 1. I know the square root of 4, it's 2. But what about the negatives? Should I be doing the negatives like we did over here? Well, no, because remember, we do not know how to take the square root of a negative unless we use our imagination. That's when we had to use those imaginary numbers, okay? So there is no negative values of that 1 or 2 when we went out that. But if it did have that, you can see it would look like a parabola on its side. So we obviously know we don't have this half of it, but just that half. And remember, if we did have this half, no longer would it be a function. Okay? So I'm just going to run through the rest of these to make sure that you guys remember. And if not, you can always do a t-chart and plot points. Okay? But the x cubed, I know 0 cubed is 0, 1 cubed is 1, -1 cubed is -1, and then 2 cubed would be all the way up there at 8. -2 cubed -8. And that's where some of these had to not have that straight line because we'd be missing a bunch of points. These are just a few sample points. Sorry, that one should not be there. Let's see if I can do that better. All right. This point should be here. So I have this elongated S shape we call a cubic function. Okay. How about everybody remember this symbol?
Absolute value.
Absolutely, very good. What does it look like?
V.
Absolute value. That's right. 0, 0. Absolute value of 1 is 1. Absolute value of 2 is 2. So it starts to look like that line that we just graphed a minute ago. That y equals x line, where everything was the exact same. But when we stuck in -1 and got -1, or -2 and got -2, or -3 and got -3, the same, what happens with the absolute value when we stick in -1, 2, or 3?
Stays positive.
That's right. So instead, we get this line, which, if you guys notice, this is kind of like that piecewise function that somebody asked about right before we started. Okay, we got one line with negative slope, and then at 0, it changes to a positive slope. I'll reiterate that point a little bit later. How about y equals e to the x? You guys know what we call these? This is called an exponential function because the x is up in the exponent. Remember, e is just a number, just like pi. It's an irrational number, okay? But with pi, you spell it pi. You got rid of the e. Well, here it is, okay? And you know pi is a little bit more than 3. That 3.14. E is a little bit less than 3. It's 2.71828, blah, 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 blah. It goes on forever. Never ends, never repeats. So you can think of E as about 3. So if we had 3 to the x, and I used my t-chart, what's the best thing to plug in up in an exponent? Everybody's favorite. How about 0? Now careful, what is anything to the 0 power?
1.
Very good. So in reality, it wouldn't matter what base I had, whether it was e exactly 3, 2, 1/2, anything to the 0 power is 1. So notice this right here is a critical point, just like the 0, 0 was in all of our others. They all shared that point in common, 0, 0, but this one does not. So what else can we plug in? Well, we definitely could plug in 1. We could plug in 2 and -1 and -2. But again, think of this as a 3 because it's really close to it. What is 3 to the first power? It's about 3. So if I wanted to graph this, I know I'm going to go up almost to 3. And if I squared it, I know that's going to be about 9. So now I'm all the way up here. Kind of resembles this right now. But careful, what happens when I plug in negatives into exponents? Which is why we call this an exponential function. Do you guys remember what happens when we have 3 to the -1?
It's smaller.
Very good. That actually moves it to the opposite side of our division bar. This is equivalent to 1/3 to the first. Okay, same thing with 3 to the -2. That's now going to take this and move it across. So I'm going to have 1/3 squared, or about 1/9. So yeah, notice they are definitely getting smaller with that negative. What's going to happen when I put in -100? I'd have 1/e to the 100th, which is what? Super small, right? But is it ever going to reach 0? No. Very good. A few of you chimed in. So we're going to have something like this. And this, I don't know if you guys remember, is where we introduced you to this weird term for a line called, anyone? Anybody remember what that border line is called? That our graph approaches but never actually touches? Alex, good, but you spelled it wrong. That's how most people want to say it, and that's how it is said. But you got to watch your mouth, okay? It is not an asymptote. It's spelled kind of weird, just like our crazy English language, right? It's got this weird silent P in there, okay? It's an asymptote. And that asymptote is just a borderline that our graph approaches, but it lets us know that, yes, it is going down, 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 but it's not doing this. It actually plateaus out, but is going to continue to get smaller and smaller and smaller. And this is something I brought up last week, that we will introduce this new thing called a limit. And you guys have actually already been introduced to it. You just never put a word with it yet. That's what our graph is approaching. Okay, so I can actually tell you that this asymptote is the line where y is equal to 0 everywhere. Does everybody agree that that's true? At this point on my line, this point, every single point, isn't y equal to 0? I'm not up or down any. My y is equal to 0 everywhere, but x obviously can be anything. So that's why we don't even mention it. Okay, so I'm going to jump down here to the last few, and I'm going to go to the, does everybody remember what LN stood for?
Natural log.
Very good. They call this the natural number. Okay, I want to help you guys remember it. So naturally, I will mention it. Okay, natural E is the natural number that with logarithms, we have to have a base down here. And if we don't put it, naturally, we will use E. Okay, everywhere else in the world, they use base what to count with?
10.
So if we don't put it with just the regular logarithm, that means it's base 10. If they put ln, which is still a logarithm, but the natural logarithm, then we will use base e to denote that. And we're going to talk about something a little bit later today. It's called inverses. And inverses, hopefully you guys remember, is when we reverse things. And that means that instead of this graph here, the inverse of it is this graph, which means instead of having an asymptote along the x-axis, we will have an asymptote along the what?
Y-axis.
Very good. And instead of the point 0, 1, what is the reverse of 0, 1?
1, 0.
Very good. 1, 0. I appreciate you all participating. Okay. And remember we talked about increasing versus decreasing? We read those left to right. Well, notice this one is definitely what from left to right. As our x's get bigger, what are our y's doing?
Increasing.
Exponentially. And you guys have heard that term a lot lately because of this pandemic. I don't know if you've heard of it. All right, COVID. It was spreading exponentially, meaning that it would grow, right? 2 or 3-fold every day, every month, every whatever. Okay. So in this case, we will still have what is called an increasing graph. So that means from here to there. All right, and we'll wrap all this up at the very end. These are two that I don't really think that you may have ever seen, some of you. Depends on your schooling, your background. All right, but 1 over x and 1 over x squared. If we don't know what they look like, let's do a little t-chart. Give me some good x values to plug in. And which one have we been plugging in a lot for like all of these so far?
0.
Plug in 0. What's the one thing that we cannot plug in for 0? Excuse me, to a fraction. That's our 0. Because what is 1 divided by 0? It does not exist. Which over here, we had this borderline for what we were approaching. This one was a horizontal, this one was a vertical line. Well, when we don't have an x value for this point here for x, that gives me a y value. How are we going to show that? How are we going to let them know that there is no y value for that x? We're going to draw our asymptote. And remember what asymptotes are just borderlines. So we know that to the right of this thing and to the left of this thing, it's either going to approach up here and go shoot up to positive infinity, or it's going to approach down here and go down to negative infinity. And same thing on the left side, positive or negative. Can you guys help me out? What would it be to the right over here? What value is this again? And what do we say 0 does on our number line? It splits the positives and negatives. Well then, if I was to plug in something like a 1, a 2, a 3, what am I going to get here? Plug in 1, I will be at 1 over 1. If I plug in 2, 1/2, 1/3. You guys get the idea, right? What is it doing?
Inversing.
Yeah, it's actually going to have an asymptote out here as well, right? But what if I actually plugged in something like, instead of 1, 2, or 3, what if I plugged in 1/2? What is 1 over 1/2? Well, I can multiply by that fancy 1 of 2 over 2. So that the 2's here cancel out, and notice all of this becomes a 1, and this gives me a value of 2. So I'll actually get the reciprocal. A lot of people get inverse and reciprocal mixed up, okay? So when I put in 1/2 as a value, I actually got 2. What about 1/100th? What is 1 divided by 100th? So you can see that it's going to shoot up to positive infinity. And what would happen, guys, if I went to the other side of 0 here? What am I going to have to plug in over here? Negative numbers, which means the only thing that's going to change with all of these values that we just found is that they're going to become what?
Negative.
So I will get basically a mirror image of this, but it will shoot down to negative infinity and still approach what value when we go to negative big numbers in the x?
0.
Very good. So I will still have this horizontal asymptote that my graph is going to approach. And I could still put in -1 and get that -1 and get it a little bit better of a graph, but you guys get the idea. So help me out. What happens when we take 1 over x and we square it? What do you think's going to happen? Do we still have that issue of 0 down here?
Yes.
So I'll still have that vertical asymptote. Will I still go up to infinity on the right side?
Yes.
Yeah, because they're positive. Will I still approach that really big number? Well, yeah, even faster because it's being squared. Will I still approach 0 when I put in those 2s and 3s? Well, yeah, even faster because it's squared. When I plug in 2 and square it now, I'm going to have 1/4. So I'm actually going to get there a whole lot faster to that 0. But what about the left side? Are we going to have the same results as we did over here, but just faster?
No.
Why? What's going to change? What happens when we square things? What always comes out?
Positive number.
Very good. So it's going to take all of these that are currently down below the y-axis, which means negatives, and it's going to move it up here. So now we will have that look. And my goal for you all by the end of this, hopefully, week, but definitely by the end of this chapter, is that anytime you are given one of those 9 functions, you can immediately see that in your head. Because guess what the name of this was? Transformations. Which means, of course, what are we going to do to each and every one of these? Transform them, move them, stretch them, shift them. We will take all of those red dots that I put on there, which I'm going to call vertex, okay, those starting places, and we're going to move that part around, set it back down, boom, do the exact same drawing. That V shape for an absolute value, this elongated S for any cube, this half of a parabola on its side for any square root function. That's not going to change. What's going to change is where we put it. And that's the gist of this section. Okay, so I wanted to have these all for you nice and simply in your notes. And I even added a few others. I put in a cube root function. So instead of the cube function being like this, you can see the cube root goes the other direction. Still increasing, like this one. Okay, what they call them and their graphs are all there in a lot better form. Okay, so again, if you want to read this, watch it back, or write down any more notes on it, once I post the recording, you can go ahead and check this out and jot down, take a screenshot, whatever you want. Okay, but notice what else is included on there that we already talked about last week.
Domain range.
Very good. The domain and range. And notice a lot of them are starting or ending at either negative or positive infinity. Some of them have to have that union to unite two different intervals or sections of numbers. Okay. Others are continuous or smooth, where we don't need that jump because it doesn't have that asymptote that we need to unite two different sides to. Okay. All right. Any questions on that so far? All right. So now that we have at least seen all of these, our objective is to know them. And our book calls them the toolkit functions, because these are the tools on your tool belt that you're going to need to know so that we can actually use them in different scenarios. Okay. I like to call them just the parent functions. These are the most basic of the basic. But of course, what we're going to do is now manipulate them. We're going to put them into different looks, and therefore the graph is also going to look different. Okay, we're going to shift either vertically or horizontally. We're going to stretch, compress, and then reflect. So I hope you guys all brought your yoga mats. Okay, because this is now what they're going to start looking like, where the A, B, H, and K are all going to be involved. The only thing that's going to change and differ is what kind of function is it. If the whole thing's being squared, parabola. If it's got, instead of that, the absolute value on it, V shape. If it's cubed, all those different things, what are they going to affect? Well, again, if you know those parent or toolkit functions, when it was, say, cubed, and you know it's this shape, we're just going to pick that point, that vertex, I'm going to call it, and we're going to do different things to it. We're going to take it and we're going to shift it right 2 and down 3. Set it back down, and then we will redraw it. Okay, things of that nature. So I'm going to give you a quick little overview of what each of these things does. And then we will start talking about it. Okay, when things are being done to the x. Remember, x's are x's because they wanted the opposite of us. Okay, just me. All right. But no, that's a good little joke to hopefully help you guys remember that whatever is being done directly to the x, notice they put a minus sign here. Because if I asked you guys to give me the opposite of, say, the number 5, what would you all tell me to put?
-5.
So see, when I asked you for this, you gave me this symbol to that thing. So that's why you can see here, we already have it set up as the opposite. Okay. So remember, x's, we're going to do the opposite of what's been done to them. Where y's are y's, we're going to do what they say. Okay, so our x value, which I'm going to highlight here, we're going to do the opposite of it. And what is being done to that x value? Well, right now it's being multiplied by b and subtracted by h. And when we're adding or subtracting, that's going to be our shifts. When we're multiplying or dividing, that's going to be our stretching or compressing down, either horizontally or vertically. Okay, so the h is going to be a shift horizontally of h. All right, it's going to be the opposite. So again, notice that is there. Where the k is not being done to the x in there, so therefore it's going to affect our y value. Okay, So that part we're going to shift in the y direction, which would therefore be vertically of exactly k. Right? So I'm going to put a little note here and make sure that you guys see it. The opposite of whatever's there. Okay, that's why that negative h is there. For A and B, that is going to be our stretching and compressing. And again, you should know which one is doing or having the effect on which variable. And so since it's being done to the x, the B is going to be a stretch or compression. Horizontally, where the other is going to be a stretch or compression of A, and that's going to be done vertically. Right, and there's one more thing that we do also need to talk about and mention, and that's kind of a case in its own. All right, and that is when we have a negative on either of those. Okay, that is going to make us have what is called a reflection. And if it's being done to the B, then it's going to affect all my x's, which means it's going to reflect about the y-axis because it's affecting all my x's, right? Where the other one is going to be a reflection about the x-axis because it's going to have the opposite effect. As we mentioned up here, that's what that symbol means for the y values. All right, so that's pretty much it for that entire section. The only thing I wanted to mention, which I kind of alluded to earlier, is this thing called an even versus odd. You guys may have heard of that, but not with graphs, more so with numbers, obviously. But how do we tell if something is even versus odd? We throw in the negative value. And that negative value for x, if it comes out when you do that, the exact same, then it's even. Think about playing a game. If the score is even, then that means it's the same, right? Where if it's the opposite, then it's going to be odd. Okay, so if you get the exact opposite of your original function by plugging in that negative, then it is going to be odd for opposite. Okay, so if you want to write something down, even, same, odd, opposite. And we're talking about plugging in that negative function and whether you get the same thing out or the opposite of that original function. And as you saw, every once in a while, and it's only special cases, this will come in very much handy towards the end of the first semester of calculus. Okay, so that's why I'm just kind of showing it to you, not going into too much detail, but you can probably guess which ones of these are even versus odd. What do you think on this one? Well, look, it's x to the first. That's odd. This is odd. This is x to the second. You get the same thing on the right as you do the left. It's what is called symmetrical about the y-axis. Okay, this one is actually symmetrical about the origin. So if I go over 3 and up 3, this one will be -3, -3. It's the exact opposite of what this is. Okay, so it's got symmetry on both sides of the origin. Another odd one right there. 2, 8, -2, -8. Okay, so again, even. There's a few different ones that we could actually test and see, but it's just something that I wanted to mention so that we can at least say that we saw it before we go into calculus. All right, 3, 6. Pretty simple. It's only going to focus on the absolute value functions. Okay, but of course, since we just talked about graphing it, we're going to do other things than just graph. So what is the definition of an absolute value?
Distance from 0.
Perfect. That's why I like math. You don't need a bunch of fluff. I don't need so many words and so many paragraphs and so many pages, as I know some of you have to deal with in your English and other classes, right? Just get to the point. Distance from 0, period. Those 3 words, that's all you need to know. But can you define what an absolute value function is as a piecewise function? If I asked you to give me the function for the absolute value, you cannot just put this. I want you to expand on that. What would I get if I chose something positive? And what would I get if I chose something negative? What do you think? If I stuck into this something that was 0 or above, what would I get out? Give me a number. Somebody give me a positive number. Give me something greater than or equal to 0.
1.
1. Way to think outside of the box. Very good. If I stuck in 1 in here and I took the absolute value, what is the distance from 0 that 1 is?
1.
Excellent. With enthusiasm. 1. Which
I got
means
kids, man. I'm tired.
I get it. I get it. What if I stuck in 2 or 3 or 2/3? Whatever I chose in this realm, I would get exactly that thing out, wouldn't I? Because the distance is always measured in positive. So whether I go 1, 2, 3, or anywhere in between, yes, I will get exactly what I put in. But careful, what if we made a negative value in there? What do I get out? I'm looking for one word.
Positive.
You're right. But how do I write that here? Because is everybody's, good Alex, is everybody's favorite number 3? No, so if I ask you to pick your favorite number, but we wanted to measure it on the left side of 0. Like Barrett said, we're going to get out the positive case of it because we're measuring distances. You've never seen a measuring tape that has negative numbers, right? The negative just tells us direction, positive to the right, negative to the left of 0. So what is always going to come out is that positive 3, but is it always going to be 3? No, that's why it varies. We put a variable. So Alex hit it on the nose. He said in the chat, -x. And what did I tell you negative meant earlier? It's the opposite. So no matter what you put in your favorite number, big, small, fraction, decimal, if it was negative, we know the absolute value, like Barrett said, would come out positive. But the way that we can say that here is the opposite. It'll come out the opposite of your -3, which is therefore that positive. Okay, and that's kind of weird because you think, well, no, can't be negative. Everything in the absolute value always comes out positive. That's wrong. But remember, we said that we were only going to plug in what? Negative values. So that's why we got to make that negative become positive by throwing a negative in front of it. Okay, so let's see if we can put these things together. Let's write an equation for the absolute value function that is horizontally shifted left 2 units, flipped vertically, and also shifted up 3 units vertically. I'll give you 30 seconds. See if you can come up with the absolute value function based on those things. Ready, go. And that's how you all should have started, obviously, right? Because they told us it was an absolute value function. But can you apply those 3 things? 1, 2, 3 to give me the finished product? And that's what I just reviewed here, just in case you weren't sure. All right, anybody want to help me with the first thing? Horizontally shifted left 2 units. Sorry, Jacob, go ahead.
Oh, I think we're going to start out on the left of the expression.
Yeah, and that's a good point. It doesn't matter. If you wanted to do the vertically flipped, what are we going to be changing if it says vertically flipped?
That'd be A, so -1.
Good, the y values. And it didn't say anything about stretching or compressing. It just said, take that normal V shape, absolute value, and flip it. So now it's going to be facing down, which happened to change all of my y values from going up to the opposite. And remember, this is the symbol we use. Do you even need the 1?
No.
So if you don't want to write it, don't worry about it. Okay? How about then the second thing?
X plus 2.
Good. Why did you do +2? Isn't left horizontally negative?
It's the opposite.
Good. Remember, x's want the opposite of us, so that's why we are going to put +2. And then how about that third thing? Shifting up. That is obviously in the y direction. Remember, y's are y's. We're going to do exactly what they say. We're going to go up 3 units. And a few of you direct message that exact thing. I appreciate you letting everyone else think for themselves. Very good. Remember, if you don't want to put the 1, you don't need to. Okay? So whether they give us this and ask us to graph it, we should know that our shift, our vertex, is going to be left 2, down 3, instead of that 0, 0 that we normally would start at. And then that negative in front is not inside with the x, so therefore it's going to affect our y values. That's what I want you guys to be able to see and do like that. Okay? Awesome. So let's take it a step further. We are in a pre-calculus class, so we're going to talk a lot about algebra, especially the first 2/3 of this class. How do we solve an absolute value equation? Well, for me, I like to narrow it down to just 2 steps. Isolate that absolute value. Get it by itself. Because what do we know the definition of absolute value is? Distance from
0.
0. Good, Barrett. And if I say, find me the absolute value of what thing is equal to 5, what would you tell me? What x values?
5 and -5.
Very good, Julian. I could go right 5 or left 5. And the distance that I would have traveled would have been 5. One's to the right, one's to the left. That's the difference between positive and negative from 0. Okay? So when they give us something like this, once we've isolated that absolute value, we're going to have to do the 2 cases, the positive and the negative distance for each. So that's it. Let's do this one very quickly. And what are they telling us to let that f of x or that y value equal? Zero. So I'm literally going to replace this with what they're telling me it's equivalent to. So I will take the absolute value of 2x minus 1 minus 3 and set it equal instead of to f of x to 0. So help me out, gang. What's the first step? Good. To keep it equal, we got to do it equally. We'll add 3 to both sides to get that to drop out. Now I got my absolute value equals 3. And up here, just like we had the 5, I could have changed it to 3. Which means whatever is inside of here has to be a 2x minus 1. I didn't even write it down yet because I want you guys to see this is the same as this. I will set whatever's inside of here equal to both 3 and -3. That's it. That's all we're doing. So I will take that 2x minus 1 and I'll do the positive case. And I'll take the 2x minus 1 and do the negative case. Because can we actually solve an equation with an absolute value in it? No. So that's why we have to isolate it, get it by itself, so that we can then use the definition of it, which is our 2 cases, the positive and negative. Now all we got to do is solve each one of these individually, which is easy money. Add 1. Now, I'm going to have to do the same thing to this one, so I'm just going to solve them simultaneously, one step at a time. Now I got 2x, careful, over here is 4, and then 2x over here is -2. All right, then what? Or just give me the answers. You guys know that 2 times what gives you 4 is 2, and then 2 times what gives you -2 is -1. And remember, because there's 2 cases, almost always you're going to get 2 answers. Okay? Everybody remember that? Again, there's lots of different backgrounds in this class. I'm trying to go slow just in case somebody's never seen this before. Hopefully, most of you have at least seen this before. If not, know it. All right? By the way, that's it for 3.6. Okay, the rest of that stuff I pretty much already covered in the first section. So they'll add some domain and range stuff, other things with absolute values, but that's the new stuff. All right. So the last thing we're going to talk about today is inverse functions. All right, then we'll take a little break if you need it and start in on our group quiz. So I mentioned this earlier. Let's see who's paying attention. What is inverse a fancy math term for? Anybody?
Flipped.
Close. They actually rhyme. Inverse, reverse. Right? If I asked you for the inverse of adding, what would you tell me?
Subtraction.
Yeah, multiplying, dividing,
Adding.
square rooting, logarithm, exponential. Everything has its kryptonite, its inverse. Okay? It has to be able to be undone. If we know how to do it, we should be able to undo it. All right? So that means when we're talking about inputs and outputs, that domain and range stuff, they also are reversed. So if I ask you for the domain of the inverse function, what is that equivalent to?
The range.
Very good. The range of the original function. Awesome. Very good. Now somebody said the opposite in the chat. That is a common mistake. A lot of people say that. They'll also say reciprocal. Okay? But make sure that you know that inverse and reverse are one and the same. Remember, opposite, we use this symbol for. Okay? So if we want to ensure that what we originally had is a function, when we take its inverse and we find that, we want to make sure that it too is a function. What do you think? How would we ensure that if we are given the original function, that the inverse would also be a function? It is called a one-to-one correspondence or function. Now, we kind of talked about this before, right? We talked about one input and only getting one output. What do you think a one-to-one function means? It means the reverse is also true. If we go 1x to 1y, we also, to be a one-to-one function, have to go 1y back to 1x. So for example, is a parabola a one-to-one function? A lot of you are saying no. How come? Is it a function? Absolutely. It passes. For every one of these x's, we're seeing that only one y would hit or be given out. But what could I draw on this to check if its inverse is going to be a function? If we use the vertical line test to see if it's a function, what would we use to see if the inverse is also going to be a function?
Horizontal.
Very good. Barrett was giving me the mustache. That's right. Horizontal. The inverse of that line, the reverse. Instead of a vertical line, we're going to use a horizontal line, and you can see that this fails. Now, could we make it to where it doesn't fail? Absolutely, and we'll talk about that in just a minute. All I'd have to do is get rid of 1/2 of it. And now, not only is it still a function, now it would also pass the horizontal line test. Very good. Awesome. So let's tie all of the entire lecture today together. What have we been talking about from the beginning? The graphs. And if you can visualize what we're dealing with, would you be able to see if it's a function or if its inverse is also going to be a function? Horizontal or vertical line test. That's why we want to make sure, to simplify things, that we can quickly recall and visualize all those graphs, as many as possible. Okay, so here's the unfortunate part. The inverse symbol, I don't know if you guys remember, is that -1. Remember, we just talked about what would happen if we had 3 to the -1 power. Well, that was equal to 1/3. So you got to make sure that you don't use this loosely and you know the difference between them wanting the reciprocal of this and knowing the inverse. And what's the big difference? One is used to a variable or a number, and the other is being done to a what?
Function.
Notice they put it after the f and not after the x. And that's because of this and us already knowing what negative exponents do. The reciprocal already. Okay? So again, be careful. That's why they put it there. It does not mean that you flip the function. Okay? It means you're going to do what to the function? Don't say inverse. Give me something better.
Reverse.
Ah, nice. That's what you need to recognize inverse as. Okay? So how do we tell if we are given two functions, whether they are indeed inverses of each other? Unfortunately, we have to go back to last week and do those composite functions that we learned. Remember that fog and Goff stuff? Some of you guys are like, fog that, I don't want to, but f of g of x, if they are indeed inverses of each other, remember what we said inverse meant? Reverse. They'll undo one another. So whatever we plug in to whatever order, whether we plug in the f and then the g, or the g and then the f, if they're inverses, they will undo each other, and whatever we put in, that's what we'll get out. Unfortunately, though, you do have to test both directions to ensure that they are indeed inverses of each other. Okay, so I'm giving you a quick example here that we can work through together and then wrap this up. What if I gave you this and this function, and I wanted to know, are they inverses of each other? What would we have to do? Just test. And remember when we were working on these last week, I reminded you all that take a look at the bigger picture. I'm going to have to do f of something. Here, g of something. So you're literally taking the g of x function, which they gave us here, and you're going to plug that into your f function. All right. So we're going to start by taking the g of x, which is the cube root of x plus 1. And now we're going to have to do f of that. So we know f of something is equal to that thing minus 1 cubed. And that thing that we were given was the g of x. So we will do the cube root of x plus 1 minus 1 cubed. And does everybody remember our order of operations? PEMDAS, right? Please excuse my dear Aunt Sally. She's gassy or whatever, right? Parentheses. Can't do anything here. Let me make that x look more like an x. And then we'll go to the next set of parentheses, which we can do something. The 1 minus the 1. Now all I have is the cube root of x, and it's asking me to cube it. And what happens when you cube something that has already been taken the cube root of? Inverse operations, right? So same thing for the other one, just to check it. F of x, we'd have to plug that in, which is the x minus 1 quantity cubed. And we know g of something already is equal to the cube root of something plus 1. And that's something that we're plugging in for this one is the x minus 1 cubed. So when you take the cube root of something cubed, again, inverse operation, you get x minus 1 out. Bring down that plus 1, they cancel. I get what I originally put in. So unfortunately, that's what we have to do to check that they are indeed inverses of one another. Okay.
Where's the one coming from again? On the outside of the
No pun
cube root?
intended, but which one are you talking about? The G or the F? Talking about over here?
Yeah, yes.
Sorry, Julian. So yeah, for this one, remember our G function is the cube root of x plus 1. So I put G of x, I put a big blank there, right? Is equal to the cube root of x plus 1.
Okay. Thank
And
you.
then they replace the whole x with another function. And so we replaced our x's with that. Yeah, it gets a little confusing, almost like a rabbit hole. It's like, well, why am I plugging this into that? And can get a little confusing for students for sure. Just remember to do your order of operations, work your way out. Okay, great question. So the last things we need to talk about within this section is what we mentioned before. How about domain and range? Barrett helped me out a little bit earlier, and he said, well, if we have the range of our original, that would be equivalent to the domain of the inverse. Or vice versa, if we knew the domain, of all of our original function, well, then that is going to be the range of the inverse. Okay, so if I gave you this drawing, this graph, which hopefully you guys recognize, looks like what?
Exponential.
Very good. Looks like an exponential function, but it looks like it's been shifted to here. Right 3, in other words. Just trying to throw a little review in. That's not our question. The question is twofold. Find G of 3 and the inverse, even though they're only giving us the function. The inverse of that. So which one of those should you be able to find immediately? Part A or part B? Part A, I agree with, for those of you that said it and put it in the chat. Why part A? Well, they gave us the graph of G. So it says to find G of 3, which means what did they give us? The X or the Y? Yeah, remember, if you're ever unsure, write it right underneath. Okay. F of X was equal to Y. Notice they gave me the X, they want the Y. So go what? Right 3 and go up or down, depending on your graph. In this case, up until you hit, and what do we get?
1.
Excellent. Now, do me a favor. Think on your own for a second. How would we answer that? And see if you can answer it. If you want to direct message me in the chat, if you already got it, go for it. Good, Alex. So good, James. Let me give you guys a little hint just in case you're kind of confused on this. Remember what we said earlier, just right above, about the domain and range of the original versus the inverse function. They're flip-flopped, aren't they? Which means if we have an X to our original function and we give them the Y, what is the inverse going to do with these? What did I tell you to remember for inverse?
Reverse.
Which means, what should I be saying this is and this? Because of that right there.
G of y equals x.
Very good. Does that help? Do you see what the inverse gave us? What do they usually tell us to put in? An input, an x. And what do we usually give them? The output, the y. But because it's inverse, that means they reversed what they're going to give us. And therefore, this is my what value?
1.
And there's my 3. I have to go right until I hit to get my x value, which would be, as many of you put in the chat, very good, 5. Does that make sense? Because it can be confusing because you do have to think in reverse order. Okay. Good. All right. So how do we find, now that we've talked about the geometric of all this, let's look more at the algebra. How do we find the inverse of a given equation? And the book has more steps. I like to just think of it as 2. Okay. But there's one important caveat that I gave you here. In order to find an inverse, it has to be a what kind of function?
1-to-1.
1-to-1 function.
Excellent job, guys. Very good. And how do we test for that? If we have the graph or we can see it?
Horizontal line test.
Very good. Awesome. So all I'm going to do is give you, if they ask you to find the inverse, well, then we're going to do the reverse. We're going to switch all the x's and all the y's. But because we all know the graphs that we did from the very beginning of today as y equals, well, then we're going to have to solve or isolate. For that, I put quote unquote new y value. New because we reversed all the x's and y's. Okay, that's my way. Let's make sure that we can do it. Here's the last thing for today, and then I'll give you guys the last bit to work on all of this together in groups. So let's first find the inverse, then state the domain and range of the inverse, and then we will graph both that function and its inverse on the same set of axes. These are all the different things that they could ask you within the section. One example. Let's do it. How are we going to do part A? How are we going to find the inverse? Well, right now I know that they gave me this y equals 2 plus square root of x minus 4. Now, if you don't like the form that that's in, you could have rewritten it as the square root of x minus 4 plus 2. Do you guys see why sometimes they'll put the 2 in front rather than at the end? Because some people will extend this out a little too far and they'll be like, well, is the 2 underneath or not? So that's why a lot of times they'll put it out in front rather than anything at the end of it. Okay, either way, I'm good. Now, I rewrote f of x as y because it's easier to write y than f of x. Okay, know that they still stand for the output. This is just more powerful. It tells me that this is a function. And does everybody know what this looks like? Could we do part C right now and graph this? Yeah, Barrett? What does it look like?
Like the square root function.
Very good. It's a square root function, which I know he was being funny because, you know, obviously it looks like a square root, just without the little hook there. You just have it looks like that, half of a parabola on its side, but it's not just the square root function. You guys see it now? Y equals square root of x. It obviously has some adding and subtracting going on. So can you tell me the new quote unquote vertex, that starting place that we would be graphing this? Very good. X's opposite, Y's are Y's. We'll do what it says. So we know that it's going to shift right 4 and up 2. What's going to shift right 4 and up 2?
The vertex.
Good. That starting point, which remember was 0, 0. We knew the square root of 0 was 0. That was our starting point. So I'm going to move this thing over 4 and up 2. And then from there, do I just go? Well, I should probably get it a little bit closer to being perfect. I know that anything to the right of this vertex, I can forget about all this now. This is my 0, 0. I just shifted it right 4 and up 2. Now I know when I went right 1 and I took the square root of that, I got 1. When I went right 4 from there, then I was able to go up 1, 2 places. Do you guys see how I'm building this exactly the same way as I did when it was just this alone? The only thing that changed is where I started. That's it. Now you guys want to see something cool? I can actually graph the inverse of this without even finding it. And here's why. I know that 0, 0, 1, 1, 2, 2, 3, 3, this right here is the graph of y equals x. Remember that? It was called the identity function because everything I plug in for x, I get the exact same thing out for y. This is your mirror when you are dealing with inverses. Have you ever seen yourself in the mirror? Or that really weird person that's looking back at you on the other side? And when you move in closer, they move in closer. And when you move out, it's always that same distance. This is our mirror. And if I know that this is my vertex, what would the inverse of this be?
It'll be 2, 4.
How'd you get that so fast? We haven't even found the inverse yet. What'd you do, Julian?
I just switched the X and the Y.
You reversed them. And notice that if we go up, over 2 and up 4, we would be right here. How about another point? This one was over 1, up 1, right? So that was the point 5, 3. So another one would be over 1, up 1. But then I'd have to go 4, 2. And notice I just built my beautiful butterfly. Can you see the wings and how they're symmetrical all the way across? So this line y equals x is always going to be our mirror for any graph and its inverse. Thank you. So now let's go quickly and solve by first switching the x and the y, because it is, after all, called the inverse, and not touching anything else. That was step 1. Switch all the x's and y's. Sometimes you'll have more than one. And now we'll solve for the new y. So now I'm gonna switch to solving. Instead of x equals, I want to get it back to my y equals. So undoing everything that's been done to it, starting by subtracting 2. Now I got the square root of y minus 4 equals x minus 2. Now I'll take that and I will square both sides to get that out of there. I'm going to leave this. I'm not going to expand it. I'm just going to leave it. And then my last step would be to add 4. And instead of putting y equals here and y equals there, or f of x and f of x, I'm going to rewrite this to let you know that, you know what, this is actually the inverse of my original function. And does everybody recognize what kind of graph this would be? Careful. Good, Barrett, showing me a parabola. Some of you chimed in on the chat, parabola, but the problem is, remember when we were down here and we said our vertex would be at 2, 4, just like we talked about earlier? This would have this other side. But remember, because we're dealing with inverses, we said it has to pass not only the vertical, but also the horizontal line test, which is why we only have half of this parabola and not the other. So how do we know to restrict it? Well, remember, I asked you to state the domain and range of the inverse function. Could we have done that before we did any of this graphing? Yes, because we knew the graph of this, like many of you said. Barrett was showing me, right? It was that half a parabola on its side. And it started at what? I think it was Julian and a few others gave me. It was that 4, 2, and we knew it looked like this. So can you give me the domain and range of that original function? Without even knowing anything about the inverse stuff? Yeah, what's the domain? When do I start hitting my x values? At 4, going to infinity. Very good. And then what about my range? When do I start hitting my y values? Including 2 all the way to infinity. And if that's the domain and range of my original function, what should we be able to give? Domain and range of my inverse. Careful, what's the domain? 2 to infinity. And what's the range? Very good. So that is it, my friends. I know it's a lot. You can see why, because this is a whole week's worth of stuff. All right. Hopefully that helps.